Maybe you can mute the notification sound, yes?
Yeah, I will do. I will do. Hello, everybody. Today in a different hour, in an exceptional hour, because of our speaker today lives very far from us. Okay, he lives in Sydney, so because of the time, the different time zone. Okay, we have our seminar in a different hour. So today it is my pleasure to introduce the Professor Amir Gandomi. He's Professor of Data Science at the University of Technology of Sydney. And we invite him because of his impressive curriculum and number of publications in the area of optimization and computational intelligence. He's a highly cited researcher for 5 consecutive years, and he also ranked in the 17th in the bibliography among more than 12,000 researchers. Amir, the Professor Gandomi, he has received multiple prestigious awards for his research excellence and impact, such as the 2022 Walter Haber Prize, which is known as the highest level mind career research award in the areas of civil engineering. So I think it's no time to continue to introduce the curriculum of Professor Gandomi, because it's our pleasure. This is the reasons because we have invited him, and it's time to listen to him. Professor, thank you very much to accept our invitation. The time is yours.
Hello, everyone. First, thanks, Salah, for the nice introduction, and thank you all for having me in your seminar. I should especially thanks Daniel, Juan, and Wentu for corresponding and sending the invitation email. So my presentation topic is about now it's the era of artificial intelligence, data science, big data, etc. And my presentation is also aligned to this direction. And I more specifically talk about technique that you may not really hear that much from it in the community. But I'm going to discuss its potential, some of its great achievement, and some of its application. You may find it suitable for your problem, and I would be happy to answer if you have any question after the presentation. And of course, feel free to drop me an email if it's not clear or I couldn't answer your question here. Okay, let's start. So before going to the technical content, I really like to pay some respect to the pioneer in the area of evolution. And first, I can start with evolution philosopher Jalaluddin Rumi, also known as Maulana. He was the poet in 13th century, and in his from his poems we can understand he believed in evolution in some sort of Darwinian sense. For example, in one of his poems, he said, "I died as a mineral and became a plant. I died as plant and rose to animal, and I died as animal and I was a man." And of course, theory of evolution based on natural selection. It's first proposed by Darwin in 1859 in his well-known book entitled On the Origin of Species. And when we talk about machine learning or evolutionary research, of course, we can go back to the root and see some pioneering work from Alan Turing. he also talked about evolutionary search and learning. In one of his articles, he mentioned there is a genetic or evolutionary search by which a combination of genes is looked for, the criterion being the survival value. So having said that, we can go to the outline of this presentation. This presentation has two main parts, as you can see. So first, I will discuss how evolutionary intelligence can be used for predictive data analytics. And I more specifically talk about one technique called genetic programming. And I will discuss some background, advantages of this method, how we can enhance this method, and how we can tweak this method for big data analytics. And in the second part, I will discuss about how evolutionary computation can be used for optimization. Probably you are more familiar with this side of evolutionary intelligence application. So I will go through it very briefly and try to brief it in three sections: techniques, application, and heuristics. So let's start with evolutionary computation for data analytics. So when we talk about predictive data analytics, first, natural computation and machine learning has some overlaps. And in these overlaps, you can find methods like neural computation or evolutionary computation. So what I'm talking about today, it's some sort of both machine learning and can be categorized as both machine learning and natural computation. We have a very good survey, so you can see it is recently published at ACM Computing Surveys. So generally, predictive data analytics tool can be classified in two classes: statistics methods, such as regression methods, or AI-based methods, such as artificial neural network. You have heard a lot from it. It's a very powerful tool. Fuzzy logic, support vector machine, and genetic programming. So this is the technique that I'm going to discuss, mainly discuss in the first part of this presentation. So when someone asks me what's genetic programming, my simplest answer is when a software with evolution as a programmer. It means evolution does the programming work in this system, and this is called genetic programming. So you can see from this broad definition, we can apply it to so many different fields. And actually, this method first proposed by Koza, and in one of his books, he listed 80-something different applications of genetic programming. But of course, predictive data analytics, it's the main applications of genetic programming. And if you look at the literature, this is mostly popular for predictive data analytics, like regression and classification. But what's genetic programming? So I can say, following the Darwinian natural selection, genetic programming tries to find relationship between inputs and outputs. So like any other evolutionary system, it has loops, which we call it generations. And in each generation or iteration, we applied evolutionary operators such as selection, crossover, and mutation. And we continue this generation until our selection criteria or stopping criteria met. So genetic programming, inspiring from Tree of Life, it's usually represented by tree structure, something like this. So in each node, you can have mathematical operators, you can have variables, or constant or logical operator, etc. So generally it has this kind of structure. And now by having such a structure, we can define crossover between two parents or two trees, or we can mutate one trees to another. So this is basically how genetic programming works. So not so technical, but I want to give you the broad picture of how this system works. But the main advantage of genetic programming is that it can find the structures of the system or model via evolution. So if we look at other systems like neural network or SVR or other machine learning techniques, we usually need to do some trial and error, and at the end of the day, we still constrained within the defined structure for that system. For example, in neural network, you always need to define some layers, find the optimum number of layers, neurons, activation function, etc. And that's how it's defined our system. We cannot go beyond that. So somehow we predefine the structure and only find some constant in the system. So, but genetic programming starts from scratch. It doesn't have any predefined structure. It only gets some mathematical operator or pool of mathematical operator or logical operator, and then tries to build a model based on this operator. One of the interesting examples of GP application was when NASA engineers used genetic programming for designing communication antenna for the ST5 mission. It's about 17 years ago, and they come up with a solution that was much better than engineered design antenna at that time. So there are some design based on engineering concept, and then genetic programming came and find the best structures for these antenna using genetic programming. Okay, sorry. Oops, sorry. Okay, and another feature of genetic programming is simplicity and explainability. So since we start from scratch and we don't have any predefined structure for genetic programming, the final genetic programming model is usually very simple in compared with other machine learning techniques. We can also control the complexity of the system some user defined criteria or using some multi-objective strategy, but that's usually much simpler than other techniques. For example, one study done by Kelly et al. In 2017 found that genetic programming with the very simple models can outperform very well-known models and deep learning models for Atari game playing, which seems it's a ground for deep learning or other machine learning techniques. But GP could outperform those in about 50 something different games. Actually, overall, not in all of them. But what was interesting is that besides outperforming those models, the GP models was very simple. For example, this model presented here, which you can see it's a very simple graph. It could outperform one deep neural network with more than 800,000 weights. So actually that also raised the question that do we really always need to go to the deep learning and very complex model, or we can maybe find a solution much simpler and even could be more effective and more accurate using a simpler model like genetic programming. And that work actually continued by Wilson et al. In 2018. And based on that, MIT Technology Review wrote an article and said, neural network have generated all the headlines, but a much more powerful approach is waiting in the wing. So what genetic programming does, it's actually making two selections for us. If you're familiar with predictive data analytics, we mainly need to make two big selections. The first one is selecting features. For example, doing some pre-processing and finding the best number of variables that gives us the best accuracy. And also we need to select the best model. Usually do some trial and error, and eventually sometimes we find one very good model and sometimes we don't find any model. For example, in this study, you can see we tried so many different models. Most of them seem disappointing, close to luck, but eventually XGBoost outperform all the models significantly. But what I'm saying from here is you need to do trial and error if you don't know what would be the best model for your system. You need to try XGBoost, SVM, random forest, deep learning, etc. And another features of genetic programming is that it's a population-based machine learning. So most of machine learning techniques are trajectory-based or single solution-based method, which means they start from one solution, most of the time random solution, and they try to improve it during iterations. However, genetic programming works with a population of solutions. So when we have a population of solutions, we can also take advantage of parallel processing, distributed system, and cloud computing. And that's how people work with genetic programming if they want to use big data or even at a smaller scale, but if they want to run it very quickly. So that's a strategy is very popular in genetic programming these days. So let's start with the first examples of genetic programming application to one of real world problems. So this example that I'm showing here is a very complex structure. It's called self-centering concentrically braced frame. So a centrically braced frame is the most well-known in the world. It has this system, but this self-centering system have several special elements like this post-tensioning bar that connect the roof to the ground. It has one adjacent column connected to the main column using some energy dissipation element, and one column can also uplift from the base. So during the earthquake, this system has a response, and its maximum response comes from the roof. So what we want to do, we need to find for this structure is its maximum response, and its maximum response during, especially maximum response during earthquake, which is actually very stochastic process. Earthquake itself is very stochastic. The structure is very complex, so the response would be very difficult to find. So this is applying Mangil earthquake to this structure. You can see how this roof drift change, and eventually at one point it's produced as a peak roof drift of this structure. So that's what we want to predict for this system. So for this system, we have two different sets of variables. First, a structural design variable like geometrical or mechanical properties of the system or a structure. And then we have earthquake intensity measures. And I have listed some of them here, but there are so many in the literature. In one paper I saw, they listed 30 something earthquake intensity measures. And for this study, I used a prototype structure. It's an office building designed for a steep soil site at LA, California. And this is the system that I'm going to model. And three elevation considered for this structure: 4-story building, 6-story building, and 8-story building. And I designed 75 different structures. And then I applied 170 earthquake to each of these structures. So then I could create a very comprehensive database. And one problem that I deal with here is how to select the best earthquake intensity measures. I told you there are so many of them. And also, earthquake itself is a very, very nonlinear phenomena. And its intensity measures may not have a direct relationship with the output that we wanted to predict. So we are all familiar with correlation coefficient that can predict give us information about linear relationship between two sets of data. So this is the downside of the correlation coefficient, because it only produces the linear relationship between two sets of data. So what I did is I modified correlation coefficient using genetic programming. So I replaced x with f of x in order to find a nonlinear relationship between x and y. And this is how I formulate the updated or enhanced correlation coefficient, which I call it evolutionary correlation coefficient. So I can show you how much improvement that I got from the correlation coefficient. So this is intensity measures, and this is the correlation coefficient, a square of correlation coefficient, and this is this is evolutionary correlation coefficient. You can, and this column shows us the improvement that happened within each of these correlation. So we somehow try to add nonlinearity to the correlation. So you can see here, sometimes we have more than 200 or 300% improvement in the correlation by using this evolutionary correlation coefficient. Anyway, using this updated correlation coefficient or evolutionary correlation coefficient, I selected the best three for the modeling, and I used a multi-objective strategy, which means I put all the solution in one pool and then listed all non-dominated solution and selected one solution from this area. Why I select one solution from this area? The answer is from here to the right, complexity increased without that much improvement in accuracy. So we usually select the solution from this area. From here to here, complexity increased, but there's no improvement, not that much improvement in the accuracy. So these are the final models for this problem based on genetic programming. You can see this is a very complex problem, but the formula is very simple. And if I use a multi-objective strategy, it even come up with a simpler solution, as I explained. And in terms of accuracy, you can see the accuracy are very high, around 97% correlation between experimental and predicted values. Another very interesting problem in engineering is inverse analysis. So usually in engineering, we do forward analysis, which means we have a system, we give input to the system, and it gives us output. This means forward analysis. But sometimes we have the system and we apply some of input and it gives us output, but we don't know the system parameters. So the unknowns here are system parameters, which means we usually don't have explicit solution for this system. So for this kind of system, we usually use AI, machine learning, or evolutionary computation. So one interesting framework that proposed by Professor Gabushi at UIUC was that if we have an unknown material, how we can find the constitutive model for that material. They said we can run two parallel finite element model, one of them force control, the other one is displacement control, then initialize one stress strain database, apply fitting one ANN model, and they put a whole this process in a very big loop of finite elements. So eventually they come up with modify the database, modify the ANN model, etc. And this is a very interesting system because if you have an unknown material, you can find its constitutive model. So what I saw in this model is, okay, it's excellent. We have unknown material. We can eventually feed one neural network to the system. But there is a problem because after fitting one neural network to the system, how we can use this neural network? Because if this is a material property, we need to take derivative. We need, for example, if you are familiar with this area of research, we need to put it in a software, finite element software, etc. So there are some difficulties to dealing with this complex system. So what I simply did, I replaced neural network in this framework with genetic programming. And now we can easily translate the genetic programming model into the simple formula. And if we have this simple formula, we can take derivative and construct the Jacobian matrix for this material. So I tested this for cantilever beam, actually truss beam with force at the end of the cantilever, and this is the force displacement curve. And this is final model for stress and strain based on Professor Gabushi's framework. And this is the genetic programming model. And this is what I found, reference model versus genetic programming model. You can see they are very close. But I can go further from here. I can put it into the test. I can put it in a general purpose material software such as Abacus or any other finite element model. So what I did is use one system with a reference model, Ramberg-Osgood model, and this is one of what genetic programming based model gave me. So this is, you can see that stress distribution, it's almost identical into those systems. And I also tested this for soil modeling or aortic modeling. You can see we got a very good results in these two other cases. As you remember, I told you, we deal with a population of solution in genetic programming. So actually people thought, okay, since we have a team of group of solution or population of solution, why don't we team up some of those best solution and then work with those instead of only working with the best solution? Yes. So I put it into the test. I wanted to predict these two properties of these rigid joints, semi-rigid joints, flexural resistance and initial rotation stiffness. And I had three different types of joints. You can see those here. And okay, so for these these are the results on the testing data. And of course, we want to see how they work on the unseen data. So this is the best model, the result of best model. And this is the result of team solution. It means team of the best solution, not the single best solution. For example, the best 20 solution or best 30 solution. And you can see for the testing, this team of solution provides better results in compared with other solution. The best solution, or these are some other model borrowed from the literature. So this gives us this fact that, of course, the best model has the best performance on training data, but on the testing data, the team of solution may provide the better solution. And actually, we kind of demonstrated that by these example. And some other people said that since we have a team of solutions, maybe we can also connect those solutions or maybe some part of the solution using regression analysis. So this was some basic things that could come up to the people's mind. Now we have so many solutions. We can pick the best one, or we can pick features from different solution and then construct one best solution or combination of solutions from these population. So to attempt, actually successful attempt could be, for example, Searson did it in the UK in 2010, and Arnaldo in a MIT Alpha Lab did in 2014. They come up with a different system of hybrid genetic programming and regression analysis. And I test this system on very complex engineering problems. This is called concrete creep prediction, which means how concrete creep during time. And it's actually a very complex problem. There are so many models in the literature. I listed 3 of them here. And this is the model that they call GC with only 5 and genetic programming only selected 5 variables for us. So as you can see, this is the system that regression analysis connect different genes together. You can see 3 genes, very simple genes are connected together using regression analysis. And with this very simple model, we outperform very complex model in the literature. You can see in terms of R squared, we really outperform those, or we have much less error for this proposed model. We also put in the test for MOOC modeling. The data set actually include signals from a forehead scanner from students. So we want to see if the students got what it was taught in the class or not. So this is a binary classification. We put it into the test, compare GP with other well-known model like LSTM, CNN, SVMs, and we found GP very accurate for this classification method. Or for COVID, we did some time history analysis, and we actually found formula for 15 most affected countries. And it was very interesting to have a formula for each of these countries for number of deaths or number of cases. But nowadays we deal with big data. We're all familiar with the 3 V's, high volume, high velocity, high variety. And For applying genetic programming for big data, we really need to come up with a cost-effective and innovative approach, because genetic programming deals with the population of solutions, so it's very time consuming, and we need to come up with an approach if we want to apply genetic programming for big data. I won't go to the detail. I know you're all familiar with the big data concept, but I want to say this is our current research applying genetic programming for big data. Generally, we follow two approaches, and we combine these two approaches. First, divide and conquer. We try to break the big problem to several sub-problems, and then applying the GP to those sub-problems. And also we can extend the genetic programming and modify it for our big data problems. So one of the simple approach actually was proposed a long time ago in 2011. So we try to use genetic programming dimension by dimension. So instead of applying it to n-dimensional problem, you apply it to n one-dimensional problem. And you know, one-dimensional problem are very, very easy to model. So that's what we did here. This is first we use it for first variable, and then second variable, and so on and so forth. And eventually we use one model to model the interaction between variables. So, here I visualize how it can work for a big data problem. This is genetic programming, and this is how it can work when we use this multi-step genetic programming, which means several one-dimensional problems. You can see it converge very fast when we use this approach, and it's very effective for big data problem. So this is another approach, one example of this multi-step genetic programming. I won't go to the detail, but these are the different functions for different steps. And comparing with the state of the art, we can see multi-step genetic programming is competitive with all this trivial noun genetic programming. And without interaction, it's competitive, and with interaction, it's almost perfect for this problem. So there are some other advancements. I won't go to detail. We also use information theory for defining sub-problems. Actually, instead of we try to use information theory in order to group the variables and apply genetic programming to different group and different smaller sub-problems. So the results was very promising. These are the results of our proposed method. This is the results of other methods proposed in the literature. You can see our method with only 100 population reached to the much better solution. The problem here was that they didn't mention the number of iterations, so we only run our method for 15 minutes to be fair in this comparison.
UTS data scientist Professor Amir Gandomi is at the forefront of a machine learning revolution, developing tools for big data solutions inspired by natural selection. Just as nature solves its problems through evolution, genetic programming produces new, improved generations of programs. Genetic programming develops programming models through evolution. Using a machine learning model is like buying an existing house, whereas genetic programming is like building one specifically tailored to your individual needs. Divide and Conquer provides big data solutions, breaking down problems and assigning the pieces to specific genes within a chromosome. Alpha Program views each individual program in a population as a chromosome, taking the best genes from each one to create an alpha program. It's a Frankenstein-like process, borrowing the best features from others to create another individual.
So this short animation gives you some quick overview regarding our current project on genetic programming for big data analytics. So we have a few minutes, and I briefly go to how we can apply evolutionary intelligence for optimization. So if you may be familiar with this topic, so I think we don't have time to go to detail. So I only try to give some of the topics here. So when we have talk about optimization algorithm, we generally have two different classes: mathematical optimization, which use derivative information or Hessian matrix, etc., and we have nature-inspired optimization or evolutionary optimization or swarm intelligence optimization, which are the global optimization method because they do not trap in local minima very easily. So they can deal with very complex problem and even different sort of constraint, and they use other strategies, and they don't use a derivative information. They use evolution, swarm behavior, or for example, annealing. There are several methods out there. You probably familiar with some of them. For example, genetic algorithm, simulated annealing, and particle swarm optimization is some of the most well-known methods out there. And there are some of them, like some of these recent algorithms that I listed here. So the one are in green are the algorithms that either I propose or I was one of the co-author of the first paper. And if you are interested, I don't go to detail, but if you are interested, please feel free to email me, and I will be happy to share the code of this algorithm. So evolutionary computation or intelligence have been very promising in real-world applications. Actually, in 90s, Boeing used it for designing their engine, or one of the pharmaceutical companies using it for the first antiviral drug for HIV. And nowadays, so many companies are using it, such Amazon using it, Google Brain using it, Uber, and so many other companies are now using evolutionary computation methods. It can be used for very large scale problem. For example, this is a problem that we solved a few years ago. It's a 35-story space tower optimization. It has more than 1,200 members and more than 900 degree of freedom. And in each member, we had 3 constraints: minimum, maximum, and buckling stress for each of these members. And we also have so many drift constraint, etc. But you can see the P3 algorithm that we use here, it's perfectly outperformed to a state of the art for this problem. And also, evolutionary computation is a very good candidate for multi-objective optimization because it can deal with different, even many different objectives that we usually deal with in a real-world problems, such as cost, quality, time, reliability, risk, etc. So in one of our recent studies, we compared 18 different evolutionary many objective algorithms for 3 well-known combinatorial problems. And we had 3, 5, and 10 objectives for each of these problems. And actually, we recently put it into the test for one of the X Prize competition. X Prize actually pandemic challenge. They wanted to find the best policy for each countries in the world, and they had 2 objectives: reduce the number of daily cases and also stringency of the plant intervention. So I led a team called Kangaroos from Australia. We became eventually one of the top 10 team and honorable mention winner of this competition. And for finding the best trade-off, we used 3, I think, evolutionary multi-objective algorithm, which was very interesting for the judges at that competition. And the final point that I would like to make is in evolutionary competition, I already told you they are derivative free, they are global, but I should mention they are generally slower than mathematical optimization problem. But these algorithms are flexible and you can use heuristics or embed your knowledge or tailor the algorithm for your own problem. And in those cases, the algorithms are enhanced a lot if you correctly embed your knowledge into the system. And the problem that you can solve, it's much better and could be much faster than mathematical optimization problem. There are so many cases right now that they can find the very black box system in a very smaller time in compared with other algorithms. So there are so many heuristics we applied. I won't go to the detail, and actually I had a few tutorial at IEEE and ACM. So if you're interested in this topic, you can also look at those presentations. I would like to thank you all for your attention and also attending my presentation. I think we have about 10 minutes for answering the questions.
Thank you very much, Amir, for your nice presentation, and I'm very interested. Okay, now it's time. It's the time of our audience. It is time for the questions. So, as usual, feel free, okay, to make question. Okay, if you want, okay, you can write on the chat when you want to make a question. For instance, we have who is? I don't see. Okay, go ahead. I can.
Daniel seems to have some questions.
Ivan, go ahead. Ivan?
Maybe you need to open,
okay.
unmute yourself, Ivan.
Sorry. How can
I think Daniel also has some question. Daniel,
yes,
could you unmute yourself?
So, Daniel, do you want to?
Yeah.
Can you speak?
Yeah, I can speak. Do you hear me?
Yes.
Yes.
Okay, perfect. First, thank a lot for your nice presentation. It's very interesting. I work a lot with meta-heuristic and sometimes with genetic programming, but sometimes I don't work with so many problems, different problems and interesting problems. It's very interesting.
Oh, thank you.
The thing is, I have several questions. Well, I only say a few ones. When you use, for instance, in genetic programming, use multi-objective, you consider the complexity of the expression. But what is the reason of that? Is because it's more efficient? Is because you have a client and you have to show them the expression to validate that?
A very good question. So there is one topic in genetic programming called BLUT. And from BLUT, they means when you want to feed a model to one data, the simplest way could be maybe adding one term or make the model more complex, yes?
Yeah.
In this case, you can find a better solution for training data, but you are not sure if it's overfitting or now, and it provide better solution for your testing data. So in in the literature, they try to come up with different idea to how to avoid this bloat, which means adding complexity to getting more accuracy on the training data. So there are so many ways. One of them could be multi-objective strategy. This is a strategy that I like because I think you can explore more from the search space. But there are some other strategies. You can, for example, control it by yourself, designing some 3 depths or maximum 3 depths for your genetic programming trees, etc. So that's the main reason we use multi-objective strategy for genetic programming. I know it's sometimes bothersome because in addition to fitness, you also need to compute complexity, yes. But at the end of the day, it could be worthwhile to do it in order to avoid the bloat problem in genetic programming.
Okay, thank you. And only other question, but is if you can, because you're more expert than me in that, in which kind of problem do you consider that genetic programming can improve other machine learning problem? I say you have a specific problem. Sometimes you have shown that genetic programming could improve better than other machine learning techniques. And which is the feature that made you think that some kind of problem could be useful for some problem could be useful use genetic programming? You have good and bad experience, or mainly good
actually,
about that?
very good question. So for example, let's say you have a problem and you want to suggest a machine learning, yes. So one of the features of genetic programming is its simplicity, yes. Yeah. And also it provides you with the explicit formula. So right now in big topic and discussion about, for example, having explicit problem, having inside knowledge, having information regarding the model or interpretability. It's a big topic. So if you have an explicit model, it could be much simpler to do that. And sometimes, for example, for those Atari game that I showed you, they come up with a very simple graphs, genetic programming graphs, that can outperform very, very complex deep learning problems. So sometimes that can even outperform super complex system with such a special structure. So if you have a small number of data, I suggest genetic programming to be tested beside other machine learning. But if you have a big data, probably genetic programming is very time consuming as another very good option. But other than that, it could be one of good candidate. And we usually don't start with one, yes? We usually test different. Yeah, so for a smaller data, we usually use genetic programming. And it's interesting when you present some formula. Sometimes, for example, if you give it to a medical people, these parameters have a meaning for them. They can see it's placed correctly. Yes, it's that's what they expected, or that's something that excites them. So that could be something that you can consider when you suggest genetic programming.
Okay, thank you a lot for your talk.
Thank you, Daniel.
Thank you very much, Danny, for your questions. So, any more questions?
I think Ivan, and if.
But Ivan, I think he doesn't want. Really, he doesn't want. But I don't know. Okay, Masood have been. Masood, can you speak or? Can you speak?
Hello, Dr. Gandomi. You
Hello.
have my
Hello,
voice.
Matthew. Yep.
Thanks for your nice presentation. I have a question. I think it's a question from my classmate Mortaza from Delft University. I think because we discussed about it before. How can we use GP for making remaining useful life metric?
For making remaining useful life metric, could
Yes.
you elaborate that? I'm not familiar.
For example, we face, for example, remaining, you know, there are some metric for evaluate the remaining useful life of, for example, jet engines in NATA's CMAPS dataset, and we speak about how can we make, for example, index for predicting remaining useful life.
I'm not really familiar with the problem, but basically, if you're looking for a structure here, or if you're looking for a prediction like regression or classification, genetic programming can be used. So if you should look at genetic programming as something like machine learning, it does what machine learning does. And beside that, it can also find structures for you. Yes. So right now, people can also use genetic programming for programming itself, because you want to find a structure between different comments, etc. So I'm not sure what exactly this problem is. Is it regression or classification, or simply finding the structure of the system? But in any of these cases, I think you can use GP. But feel free to drop me an email with more detail, and probably I can I can provide you with more feedback.
Thanks, sir. And I have another question about the performance of GP when the number of input variables are high. For example, when we have 26 input parameters, not just, I mean, for example, you show us you did a feature selection, but and you then you generate a mathematical expression. But in some cases, especially in civil engineering cases, the final mathematical expression is so complex.
Yes.
How can we say that this new model is superior than, for example, empirical relation that's obtained, for example, from regression models? How can how can we say this is superior, this is better, not just based on performance indices, about the simplicity?
Okay, so basically, so we here say that evolution try to improve the system. Yes. So if we put accuracy as a metric, evolution try to improve the accuracy. If you put complexity as a metric, evolution try to simplify your model. But at the end of the day, this is the techniques that can be even started. For example, regression can be a starting point for genetic programming. For example, the system that I showed you that developed at MIT, they use linear regression for initialization, which means we always improve and build a model up on regression analysis. And I want to go back to your first point. You said for how many data we can use genetic programming. So you should know that genetic programming try to fit the model and also find the best structure for the model. So when we say find the best structure, it means search space is very vast. It's so many possible structures, yes? So this is now the problem, it's so difficult. So that's why we tell you, try to use it for lower number of data, or maybe somehow, as you saw in my example, select some of the features beforehand. So, okay, so, but in terms of saying how many variables, maybe the rule of thumb, it could be less than 20, or the lower the structure finds better. But if you're working in machine learning or data analytics, the complexity, one of the complexity source is dimension. We have some problem with 4 variables, but they are much more complex than a problem with 100 variables. So this is not the only source of complexity. So I cannot tell you if it can be used for your problem or not. Sometimes the landscape is very easy. You can, for 100 variables, use GP. Sometimes not. Sometimes you have 5 or 10 variables, but the landscape is super complex and it's very difficult to use other machine learning, let alone genetic programming.
Thank you, sir. Thanks for your reply.
Thank you.
Thank you very much, Masood, for your questions. So, are there any more questions?
Hello, may I ask a question?
Yeah.
Yep.
Go ahead.
First of all, thank you for your presentation. I have a question about the relation between deep genetic programming with reinforcement learning, because I feel there's a close connection between them, because, you know, if you kind of consider similarity between state actions with, you know, kind of selection of, for example, mathematical operations in genetic programming, because genetic programming seems try to select the best operations and inputs, let's say input features, to combine them based on the kind of reward, right? So what do you think? How can we kind of compare them? This is a kind of, let's say, genetic program is a kind of reinforcement learning, or vice versa?
Okay, so I should say genetic programming is mostly predictive data analytics, but reinforcement learning is different, because we want to find the policy, and we usually don't have that much clear goal function, yes, in reinforcement learning. For example, in reinforcement learning, we try to find the best policies, but we usually do not try to develop the best goal function within the system. So what area could be, if you want to take best features from these two systems and combine them, is combining genetic programming with reinforcement learning in order to find the best goal function for example, reinforcement learning. But I should say they have some similarities, but genetic programming is mostly predictive data analytics rather than reinforcement learning.
Okay, thank you very much. Because
Thank
before
you,
that,
Murtaza.
yeah, I thought we can say, okay, policy, for example, if we consider different action like plus, minus, division, multiplication, and for example, sign function, etc. These are our actions, and at the end, let's say we kind of define a policy like the resulted function, right? In reinforcement learning, I mean, considering something like genetic programming. So, okay,
yes,
I got.
But in reinforcement learning, we don't try to build any structure, yes?
You
The
mean
structure,
when you say a structure, you mean the function?
no, we usually have those connections, yes, in
Yeah.
reinforcement learning, which means we predefined one structure for the system, and now we try to play with the mathematical operators or play with different prompters in order to improve the system. Yes, but
Yeah.
here what we claim in genetic programming is that we don't have that structure. We don't have that connections. Yes.
Yes, right. Yeah, right. In reinforcement learning, we need to kind of define beforehand
Yeah.
everything.
Yeah.
All right. All right. Thank you. Thank you very much.
Thank you.
Thank you very much, Morteza. Any more questions? Okay. If there are no more questions, okay, I think that it's time to finish the presentation because we cannot want to steal more time to Professor Amir. So thank you very much again. I reiterate my thanks to Professor Amir, and I hope that we continue our relation, that this seminar will be the beginning of a collaboration with you, our researchers in DaSCI, and I hope that you you took a good time with us. Okay.
Yeah, I would like
you enjoy your time with us.
Yeah, I would like to say also, Professor Amir, that the last day weeks I was reading your several proposals more recent. I love a lot. I like a lot of your proposal of algorithm. They are my specialty. I love several algorithms that you are co-author of them. There are so many proposals in the literature in metaphoristics that are very similar. They only differ on the natural inspiration metaphor, but actually many of your proposals are really different from a study, from algorithmic point of view. I love that.
Thank you so much, Daniel. It was really nice to have a presentation here, and I really thank you for having me here. It's a nice atmosphere, and it's great you all familiar with these areas and ask very good and nice technical questions. Of course, it's very pleasure to work with you and be in touch. And let's maybe have some brainstorm sometimes when you come back from your break, and we can keep it going after that.
Okay. Yeah, it will be nice.
Thank you.
Thank you for your time also.
Thank you for having me.
Thank you, Professor Amir. And now I have a message for all our audience. Okay, this is the last webinar or the last seminar in this course in 2022. Okay, this 2021, 2022. We will start in October, I guess, a new season of webinars, and I hope that we can invite the top researchers in the world in order that motivates you to keep researching and to keep doing your best. Okay, good summer, a good holiday, because I know that you have done very hard work this year. So, and thank you very much to participate in all our webinars. So, bye-bye. Bye-bye.